we've talked about pressure, and when the force applied to a region is constant or uniform, then pressure is not a particularly complicated calculation. We said our pressure was going to be a force over an area. I want to run through an example of this. You are on board a plane, and that is cruising along pretty high up. So you're cruising along, and you find on one of these windows there's going to be a pressure difference. So let's grab one of these windows. We've got a window maybe like this. The window is 30 centimeters across and 50 centimeters tall. It's a big window. And we would like to say outside the plane, because we're pretty high up, we're going to have maybe 30 kilopascal pressure. Inside the plane, we're going to have maybe 100 kilopascal pressure inside. And I would like to know, what is the force on my window? So looking at my window, I have 30 kilopascals of pressure out here, which means the air out here is pushing on my window. But on the inside of the plane, I have 100,000 pascals, 100 kilopascals. And the air is pushing on there, so the net force on this window is going to be directed outward. The net pressure on the window is going to be 100 kilopascals minus 30 kilopascals is 70 kilopascals. And now if I'm looking for the force, I know that pressure equals force over area, so my force must be my pressure times my area. I'm going to have 70 kilopascals, so times 10 to the third. Pascals are newtons per square meter. I need to multiply that by my area. Area is length times width, so 0.5 meters times 0.3 meters on this huge window. And I get a total force of 0.5 times 0.3 is 0.15 square meters times 70 times 10 to the third. The times 10 to the third is going to be 1, 2 is 150. Another 0 is 1500 times 7. That gives me 10,500. And that will be in newtons. It's a lot of force, but that's also why these windows are so strong. I would like to do one more example of this. So let's say instead of in an airplane, instead of going up, let's go down. Maybe we're in a submarine. So maybe we have a submarine, and this submarine is way underwater. Now at a depth of about 200 meters, we get a water pressure that is about 2 million pascals. This is actually very realistic sort of number. We'll start talking about depth pressure in just a little bit. It's one of the next couple sections. But at a depth of 200 meters, which is a depth that a submarine can go, we get a water pressure of about 2 million pascals. Let's take a look at what happens to one of these hatches, maybe. So maybe we have this hatch, and this is going to have a radius of about 40 centimeters. A radius of about 40 centimeters means we get an area of pi r squared. Works out to be about a half of a square meter. So then, looking at this hatch, we've got this, and we have water pressure pushing down on it. If we wanted to find the force, we would say pressure is force over area. So our force is going to be a pressure times an area. We've got a pressure of 2 times 10 to the 6th pascals. Remember, a pascal is a Newton per square meter. We are going to multiply that by our area of half a square meter, and we get 1 times 10 to the 6th newtons, 1,000,000 newtons. Huge force. But this is actually based on real numbers. The hatches and the body, like the hull of a submarine, are really strong. They have to be to withstand that kind of pressure. Submarines will dive considerably farther than this also, so this isn't like a limiting sort of value. That's why they are made of high strength steel and sometimes titanium alloys.